Partitioning methods. So for clustering for partitions, we are trying to group objects together based on similarity distance. And so we have a data set of n objects, and we want to partition across k number of clusters. And so we want to split and have a way to calculate the similarity in distance between these objects to assign x number of objects or n number of objects to k clusters. So one brute force approach would be to have k and then go through all the different possibilities for any object that you can go into one of the k clusters. But the complexity of that becomes really huge. So essentially k times k times k up to n times. So the order there would be k to the n, so that's an exponential. And that takes a long time. So we want to find a better approach or more efficient approach, and finding the global optimal would be enumerating all the partitions, but we may not be able to do that, and we might find something that's just good enough. So even with the brute force approach, guarantee finding the global optimal is just not feasible. So we need more of a greedy approach. So we're going to look at two heuristic methods, k-means and k-medoids, that it might find the global optimal, but it may not, but it'll be good enough for us to work forward with that. And so k-means we're clustering based on the mean, which is the centroid that we'll calculate, and k-medoids, the difference is the cluster is represented by the medoid. So it chooses one of the objects to be the centroid instead of a calculated mean. So the k-means algorithm, there's 4 steps. First, you want to partition your objects into k clusters. So you're going to divide up your objects and just pick at random k centroids. You can use your domain knowledge to help in that initial assignment of the centroids. And then you're going to assign the objects to each of the closest cluster, and then compute the mean of the centroid of each cluster. So once we have the mean, then we want to go back through each of our objects and update and assign them to the closest centroid, because that centroid may have moved. So here initially was over here, and so these objects were in the initial cluster, but once we calculate the mean, then we move the centroid, and so then these objects may change its belonging to a different cluster. So once we've done that, then we go back to step 2 and calculate the mean again. So we determine the centroid, and then we go through all the objects and reassign them to the closest centroid. And essentially you're supposed to stop when the centroids don't change, so everything's converged. That's the ideal case. But sometimes that's, again, inefficient because you just keep going on for these slight changes, but it's mostly stabilized. And so then we can stop early, so where it's mostly there. So k-means we're using numerical values and not categorical. So let's take a look at this example through an example initial data set. And so let's say we had k equals 2. So we define k in advance. That's one thing with the k-means for clustering, is we define the number of clusters in advance. And so now we arbitrarily divide up our objects into 2 different clusters, and then we're going to calculate where the centroids are. So you can see we've got the black dot here for the centroid and the blue dot for the second cluster. So once we have that, we can reassign our objects. So we can go through each object and calculate the distance to the black dot cluster centroid and the blue dot centroid, and figure out where each object really should belong. And so you already see at least one object being reassigned to a different cluster. So after that, then we want to update. Once we've reassigned, we re-update the centroid, and then we repeat the process. So we continue to loop until no more changes or very little changes left. So the strengths of k-means, it's relatively efficient compared to the exponential. Here we've got our big O notation with the n for the objects, the clusters, and the number of iterations. So it's fairly efficient, it's widely used, and for the most part, I almost always start with k-means clustering. And for greedy, so we may or may not find that global optimal. It may only be a local optimal, but that's probably okay. It's going to be good enough. So what happens if you don't know K in advance? Well, that's when you want to use some domain knowledge to try to determine K or what K would work. And you could try different K values, so number of clusters, because you do have to define the number of clusters up front. Now there are some weaknesses where the k-means, it doesn't work on fancy non-convex shapes like this. So while k-means could probably find the inner circles inside here, it wouldn't be able to get this outer circle in here. So that's what we're going to look at, density-based methods for clustering it to handle situations like this. And k-means can be very sensitive to noise and outliers. And so we're going to see an example of that and compare that to k-medoids, which can help handle that situation. So in this example here, we have k-means and k-medoids we want to compare. And so if this was our data set, you can see there's an outlier kind of or noise up here. And remember with k-means, part of our process was to, if this was our, let's say this was one cluster, we need to calculate the centroid, which is the mean. So we calculate the distance between these, and then what will happen is this outlier may skew the centroid to be a little bit further out over here. And if that's noise, and it's not actually really belonging to this cluster, then we kind of have a false centroid. It's not really in the center of this particular cluster here. As opposed to the other option we're going to look at is k-medoids, which is a similar type style as the k-means, but instead of calculating the mean, what we're going to do is pick out one of these objects to represent the centroid. So it's not the calculation, it would be something like we're going to choose this particular object to represent as the centroid. And so k-medoids is going to be less affected by this outlier out here. So k-means very sensitive to outliers or noise that may be out there, and which distorts the values. K-medoids, we're using that object to represent the centroid, and so it's going to be less affected by these outliers or noise than k-means. Now, to iterate through, though, what's going to happen is when we calculate which object should be the centroid for k-medoids, it can be very computationally expensive. So it's more time-consuming to iterate through. All right, so k-medoids clustering, this partitioning around medoids, so picking that center as one of the objects. So PAM is one algorithm to help find the local minimum for the k-medoids problem. And again, it may not be the optimal, but it's faster than an exhaustive search. And so we're using the actual objects themselves to select the centroid, and it's more work than k-means because calculating the mean is quite faster and quite a bit easier than necessarily going through all the details for k-medoids. We're not going to go into too much detail. There's a couple other algorithms similar to this, Clara and Clarence, but let's take a look at an example of PAM walking through some points. So here, again, just like k-means, we do define k up front. And so we select an object as the centroids, all right, as opposed to a point. And then we assign objects to the closest medoid. And then we randomly select a non-medoid object and then compute the total cost of swapping. So what does it mean if we were to choose a different object as the medoid, like this guy, for the medoid for this cluster? Would that be a better choice than the one we currently have? So that's where the computation becomes very expensive. And then if it is a better one, then we would swap that medoid and then go back through, similar to the k-means, and check all the objects again, reassign them to the appropriate clusters, and then look again for swapping medoids until we have a convergence, or at least a convergence criterion satisfied, so that's good enough.